So what we're starting to learn about in this chapter are exponential functions. And when you learn about exponential functions, one thing you know that's always coming down the line are log functions, because you know when you add something, isn't the inverse of adding something subtracting something? If I want to undo exponential functions and solve them, I need something called logarithms. So we're going to be doing logarithms probably really soon. Probably in chapter 7, I'm going to guess we're going to get to, nope, we get to them in this chapter. So we're going to be doing all kinds of new stuff in this chapter. These are kind of a different sort of thing than you've ever messed with before, okay? Now, this is kind of your general equation here of an exponential function. It can get more complicated than this, but here's an example of an exponential function, y equal 2 to the x. What do you notice about where the x is now? It is on the... It's on the exponent. We've always had stuff that looked like y equal x squared, where the x was not, the x was just down here, but now what happens is our exponent becomes our variable, okay? So we're going to be just playing around with stuff. You could graph these functions by making a table of values and graphing them, and sometime today, after I get off the video, I'll probably pull up a graphing calculator and let us look at some stuff. So we're going to go through this. This is an exploratory section here where we're just playing around with stuff.
Can we really play with get like toys?
You're a baby.
Okay, so here we go. Let f of x equal 2 to the x power. Remember, when I have f of x equals something, I can always cross that f of x out and think of it as a y if I like that better, okay? So what I can do is I can build a table over here, and I can plug in different x's and get the y's that go with them. Have you ever heard somebody say something is just growing exponentially? Like maybe you hear the national debt is growing exponentially. That means it's growing way faster than just adding or multiplying, okay?
They're like 6 trillion in debt, right?
I don't know.
More than that.
All right.
18 trillion.
Yeah, I think it's a lot. Probably hundreds of trillions. All right, but getting on to this, they want us in number 1 to find f of 4, f of 3, f of 2, and f of 1. What does it mean when they put that number in the parentheses and they've got an f in front of it? What are they asking me to do here?
F of x is just y.
Okay, it is y, but what they're telling me, when they tell me f of 4, it means they want me to plug x is 4 in and find the y that goes with it, okay? It's just a way of saying your x is 4, plug it in and get the y that goes with it. So if I plug that in, 2 to the x is the exponent, so I'm going to plug the 4 in for the x here, because here it is. 2 to the 4th is 16, okay? Now f of 3 means take x is 3 and plug that 3 in as your exponent. What's 2 cubed? 8.
Is that a 2?
It's the best I can do with the stylus. There's a 3 here, okay? So part of it is you're going to have to listen because it doesn't always, come across the way I want, and I can't go back and erase it. Now if I plug in a 2, 2 to the x would be 2 to the second power, and that would be 4. And if I plug in 1, 2 to the first power would be 2. Now if we went and we graphed this just by hand, we could always graph any equation you want to graph. You can always do this. You can always find some points by hand and plug them in and graph them. So if x is 1, x is 2, x is 3, and x is 4, let me graph this, and I can see my numbers are growing pretty quickly. So let me go 2, 4, I'm going to count by 2s, 2, 4, 6, 8, 10, 12, 14, 16. So I'm counting by 2s here on my y-axis. If I graph that first point, I have x is 4, y is 16. 2, 4, 6, 8, 10, 12, 14, 16. X is 4, y is 16 would be over here. Because this is where 16 is up here. Okay, my next x I plugged in was 3, and when x is 3, y is 8. So here's 3. 8 would be about here. Again, if I had a better piece of graph paper, it would be lovely. Just trying to use what I have here. The next point I have would be x is 2, y is 4. So 2, 4 would be about right here. And then if x is 1, y is 2 would be about here. This is not a line. We are not in Kansas anymore, Dorothy, okay? So what we end up with is it's a curve and it does something like this. So we're going to have equations that look like this, and we're going to learn all kinds of things about them. You need to be writing this down. You're going to turn it in. As your 6.1, we're just discovering it together and discussing things, okay? What if we had plugged in x is 0? I want to talk about that because it's a very important point on this graph. What is 2 to the 0 power?
0.
Anything to the 0 power is actually 1. Anything to the 0 power is 1. So at 0, it would be 0, 1. When I drew that, I didn't have that point, and I just kind of free-handed it, but it really should come down a little lower here. So there's some stuff going on here that we need to talk about. Anytime you graph a basic exponential equation, it always goes through the point 0, 1, because no matter what your base is, if I plug in x is 0, anything to the 0 power is going to be 1. So on exponential equations, you always have the point 0, 1 on them, as long as they're just these simple ones. Now you can do something, putting other numbers on there that are going to change that.
What about if you get into negatives?
If you get into negatives, we could put -1 in there. Let's put -1 in there. 2 to the -1 power would be 1. Remember, a negative exponent moves the term to the other side to make the exponent positive. So -1, we would be at 1/2. So if -1 is here, it would be a positive 1/2. It'd be about right there, which is, kind of generally, you can kind of see it's on my graph. You can get a better picture of this if you use your calculator. We'll look at something in a minute. So now they want me to do this. They want me to look at this and notice what's going on here. Look at my table over here. Number 2 is saying, look at what's happening here. To get from 6 to 8, I could say divide by 2, but couldn't I also, isn't divide by 2 the same thing as multiplying by 1/2? Right? Okay. From 8 to 4, I could say divide by 2, but if I want to express that as multiplication, wouldn't it be multiply by 1/2? And from 4 to 2, 4 divided by 2 is 2, but I could also say that's multiply by 1/2. Okay. So we've plotted it, already, so we've already done that part. I'm going to talk about what's happening on this graph. Do y'all see how this graph, tried to scribble out the part where I graphed it too high. That green graph, do you see how it's getting really close to the x-axis? It's never going to cross it, okay? It's never going to cross it at all. As a matter of fact, right here, we could say that our x-axis right here, I'll outline the axis in red, that's the x-axis. Our x-axis is what we call, and does anybody remember what you call it when a graph gets really close to a line but it doesn't cross it? Never really gets there? It's called an asymptote. It's spelled funny, you pronounce it asymptote. The P is silent. So we have an asymptote here.
It sounds funny.
Okay. So now Caleb had asked us what happens if I plug in a negative value. If I plugged in x is -1, I got 2 to the -1, which is 1/2. Let's do some more of those. What if I plug in x is, I'll get back to black here, -2. It would be 2 to the -2 power. Now a negative exponent, you remember the little analogy we had when we talked about this sort of stuff in earlier years was the exponent is not happy with his seating arrangement. He wants to be on the other side of the fraction bar. So right now he's on the top, but if I move the whole term to the bottom, then he becomes happy and he changes to a positive sign. Basically, if you've got a negative exponent, draw a fraction bar, move the term to the other side of the fraction bar, and that will make the exponent positive when you do that. Now, since it moved off of there, we fill in with a 1. So when x is -2, y is 1/4. When it was -1, it was 1/2. Now at -2, it's down to 1/4. If I made it -3, 2 to the -3 would give me an 8. It's getting closer and closer to this line, but it's never going to touch it. There are no negative values in this basic kind of graph. Okay? in this graph, we could take and we could scoot this graph up or down or left or right by adding and subtracting things from it, or even we could multiply it by something. But we would say this most basic function up here is we call it the parent function because it's the simplest function of a certain type. It's the simplest function with a base 2. So it's a parent function.
Are there such thing as
I wanted to evaluate some of these expressions in the calculator. Let's say I wanted to plug in x is -4. Remember, my function is y equal 2 to the x power. So if I plugged in -4, it would be 2 to the -4th power. I could evaluate that by hand. I could say, okay, draw a fraction bar, move the 2 to the 4th to the other side and make the exponent positive, and then just fill in with this 1. It would be 1/16. I can also put this in my calculator though. I can say 2, if I want to type it in my calculator. If I want to raise something to a power, I need that little housetop symbol. And I'll need to put -4 in parentheses. Remember, the negative is on the bottom row of the keys. You don't want to hit the subtraction sign or the calculator is going to say error. I don't know what you're talking about here. 2 to the -4 would end up being 1/16 and whatever that divides out to. Remember, your calculator is going to give you a decimal value. But if you want to get the 1/16 when you get the decimal value, remember that you can hit math, enter, and it will change it into the reduced fraction for you.